Hi, my name is Divya Joshi and this is Zoe Villamar, and for our final project we investigated machine learning techniques used in the classification and characterization of electromyography patterns. Electromyography refers to a type of biomedical signal used in measuring neuromuscular activity. It does so by measuring changes in voltage in the muscle during active contraction of a muscle, which in turn sheds light onto the neural drive sent to the contracted muscle. Key features of an EMG signal are the duration, peak-to-peak amplitude, and the number of phases. Neuromuscular pathologies cause deviations from the normal values of these EMG characteristics. Therefore, classification of EMG patterns into different neuropathies and myopathies can be important in automated analysis and ultimately diagnostic purposes. Additionally, EMG is often used in myoelectric control of prosthetic limbs, as variations in the EMG signal are used to control for degrees of movement in prosthetics. Characterization of the EMG signal is important in use for prosthetic limbs. First, surface electrodes are attached to the skin right above the muscle of interest. Once there is an electrical depolarization when a muscle action potential passes through the muscle, the electrode picks up the change in voltage. This change is amplified, and then the signal is pre-processed using filters and other algorithms. An autoregression model is used to extract the key features, and then various classification techniques can be applied to categorize the EMG features into certain pathologies. We will go over various successful machine learning techniques that have been used in this classification. Wavelet neural networks are a type of artificial neural network and work by using a mother wavelet function as the activation function for the classification algorithm. Because this takes into account the oscillatory properties of waves, this technique has high time frequency resolution as well as a fast learning ability. A study done by Subasi et al. Found that a WNN model had a 90% success rate in classification of neuropathies and myopathies. Wavelet neural networks are beneficial as the wavelet property allows for consideration of the fast transient changes that are often present in the EMG signals.
A support vector machine works by finding the most optimal hyperplane in an n-dimensional space where there are n features to completely and accurately separate classes. There's a training set and a testing set. Kara et al. Explored a multi-class support vector machine model with a one-against-all strategy, in which classification for each data point occurs between it and the other remaining data points. They got a success rate of 100% when trying to classify neuropathies and myopathies, but this may have been due to the low sample number. Overall, support vector machines have been shown to be successful classification models when applied to neuromuscular pathologies. A new class of machine learning algorithms which has potential for EMG characterization is emerging. These are hybrid algorithms, the most notable ones being the ones that include fuzzy logic. A fuzzy system is one that handles qualitative data to make inferences. Here on the left we have what is called a neurofuzzy system, in which there's a 3-layer feed-forward artificial neural network with the middle layer using fuzzy rules. They achieved an accuracy of 90%. In a hybrid study by Z et al., they used a fusing classifier where you have a training set and a testing set. The output in each network of corresponding feature sets presents evidence about the final diagnosis from EMG classification. After training the 3 neural networks, you get the accuracy of each set, shown in the table. Then, using the outputs and diagnosis accuracy of each neural network, the consensus diagnosis result is calculated through fuzzy integral. The final accuracy is also shown in the table. We've so far discussed several noteworthy machine learning algorithms used in EMG classification or characterization. These are wavelet neural networks and support vector machines. We've also discussed a couple hybrid systems that use fuzzy rules which have achieved high accuracy. Overall, 3 aspects of machine learning algorithms should be considered. There should be a high accuracy, as we saw with the support vector machine example, a good learnability, as we saw with the wavelet neural network, and a high transparency, such as in the hybrids using fuzzy logic. An algorithm that does well in all of these will prove useful in EMG characterization to be used for either diagnosis of neuromuscular diseases or myoelectric prosthetic control.